Welcome to our critical design review presentation. Our project is WattsWatch Power Logger. We are group number 23, and this is a project sponsored by EchoEd Corp. Our team is composed of myself, Daniel Fernandez, electrical engineering, Juan Perez, electrical engineering, Boris Alvarado, electrical engineering, and Ethan Sneed, a computer engineering. So the motivation for this project comes from my background on the electrical industry. So currently, if a new load is being added into a panel, such an EV charger, the existing requirement based on the National Electrical Code 220.87 is that we have a load study of the panel, or an exception to this rule is that we can provide a 30-day load monitoring from the panel. Uh, ex- the existing system requires a technician to go install a power logger, as is shown on the picture here, uh, and have that power logger installed there for 30 days, and then pick it up when necessary. So this process takes between 6 to 8 weeks. By the time it gets installed, the 30 days go past, and it gets picked up, and the study is reviewed. At this point, the project is not even started yet. So the idea of our project is to have constant monitoring, so that at any point that the 30-day report for the NEC compliance is needed, you can access an updated report, and this will help with the growing demand to EV chargers, as those are very high consuming loads on electrical panels, and also the race for energy efficient that a lot of companies are going after right now. So the goals and objectives for our project are the following. Firstly, our device will be able to take input of one-phase or three-phase systems, a 120 and 208 system, and or 120 and 240 volt system. And we have these two voltages in order to comply with the standard voltages for residential and commercial settings. The device will constantly record voltage and readings, and then it will take the average of those readings in a 15-minute period, and that average will be sent to the MCU to keep, or to the cloud server to keep in the storage for the 30-day report. The device will use this voltage and current readings in order to generate the power consumptions and store it alongside the 15-minute data on the report in order to be used for the report. The website will be able to communicate with devices that are connected via Wi-Fi in order to allow to extract any necessary data from anywhere that there's a Wi-Fi connection. And lastly, the website will be able to generate a 30-day report that will be usable to comply with the NEC code. Our engineering specifications come from our goals and objectives. The first one is our maximum input voltage will be 240 volts AC in order to comply with the higher of the two between residential and commercial voltage, which in this case is a residential at 120 volts and 240 volts. The next one is our input and AC phases. It's going to be one phase 3 wires and three phase 4 wires, both of them at 60 hertz, which comply with the standard US electrical service. And lastly, we will have an accurate timekeeping. We need to keep less than 5 minutes difference from the global clock in order to know when the peaks are happening, as not only knowing what the peak value is, but also knowing when they happen is really important, as this can lead to changes to the system in order to lower your peaks.
Okay, here we have our hardware block diagram. Our system is powered by an AC source that's connected to a panel. Our panel is providing power to several voltage and current measuring circuits according to the number of phases. That transmits data to the MCU and to the SD card and the Wi-Fi chip, which is already integrated into the MCU. We also have power that is passing through to the battery unit. This acts as a sensor to check if the AC source is providing power. If it is, it will go through the regulators to stabilize the voltage for the MCU and the SD card. For our first hardware selection, we compared the power supply and the transformer. We chose the power supply over the transformer because of its complexity. It has an all-in-one design, and it was more compact compared to if we were to use a transformer. The transformer requires a lot more external factors such as a rectifier and voltage regulators. So in this case, we decided to go with the power supply. More specifically, we went with the IRM 15.5, which supports a universal input voltage range of 85 volts to 305 volts AC, and stabilizes that voltage to a fixed 5 volt DC 3 amp output. For our second hardware selection, we compared microcontrollers. The microcontroller we selected is the ESP32. This choice was pivotal due to its robust performance, integrated Wi-Fi and Bluetooth, and extremely low power consumption with just 5 microamps in deep sleep mode. We evaluated several other options, but the ESP32 stood out due to its combination of processing power, GPIO count, real-time performance, and low cost with only about $5. It also supports for essential communication protocols like SPI, I2C, and UART, ensuring seamless integration with our sensors and peripherals. For current measurement, we select the ASR Rogowski coils. One of the biggest benefits of this selection is the ease of installation. They're non-intrusive and don't require power to be shut down to the panel, which is critical for the usability in real-world environments. These coils offer large window sizes, allowing us to capture current from multiple conductors simultaneously, and the clip-on locking mechanism adds an extra level of safety for permanent installations. For voltage measurement, we selected insulated alligator clips. This configuration gives us high adaptability, allowing our probes to connect to various bus bar sizes inside commercial panels. The insulation on the clips plays a critical safety role and reduces the risk of arc flash and accidental shorts during installation and operation.
Here we are looking at the current measuring circuit. On the top left we have the schematic. On the top right is the breadboard prototype. Bottom left is the simulation results. And on the bottom right is the oscilloscope readings for the breadboard prototype. The circuit takes the input of the Rogowski coils and sends it through two different op-amp gain phases and adds a 2-volt DC bias. It needs the DC bias because the ADC on the ESP32 can't read values that is below 0 volts. So in the simulation results, we can see that it had a peak of 3 volts and is centered around 2 volts. And on the oscilloscope results, we got a peak result of about 2.8 volts, and it is also centered around 2 volts. Shown here is the voltage measuring circuit. On the top left, the circuit schematic. Top right, the breadboard prototype. Bottom left, the simulation waveform. And on the bottom right, the oscilloscope results from the breadboard testing. The circuit is drawing power from the panel line and neutral. It goes through a voltage transformer in order to bring the voltage down to a millivolts range, which is safe for us to handle and safe for the ESP32. Then it goes through 2 op amps in order to add gain and to include a 2-volt DC bias. On the simulation results, we had a max waveform peak of 2.9 volts, and it is centered around 2 volts. And on the oscilloscope testing, we had a peak of 3 volts and was centered around 2 volts.
So to test our current transformers, we installed it in an existing 120 to 140 volt electrical panel and tested what the integrator voltage was on the output of it. In order to do this, we connected the integrator to a 9-volt battery to power it up. We collected a measurement from the panel with our handheld meter, and we collected the measurement from the output of the integrator with a handheld oscilloscope. After this, we compared the results, and we found they were very consistent. To show why we are using alligator clips for our voltage measurement device for this project, we made the video on the right. First of all, it shows why it's important to use insulated alligator clips in electrical panels, as there's a lot of metal parts and any touching of those can cause an arc flash. It shows the versatility of alligator clips, as they can be installed in different size electrical lugs and even bus bars if necessary. And it shows that after the connections are done, they are secure, which allows us to have a permanent logger installed without fear of some connections falling off.
Here is the schematic for the main PCB. We have on this section 3 voltage measuring circuits. Over here is 3 current measuring circuits. This portion is the MCU, the battery backup power path system, and then the rest are peripherals and connections for the current transformers and for the voltage leads. Here's the main PCB. On the black portion on the top, it has all the high voltage components separated from the rest of the low voltage components. There'll be a piece of plexiglass covering the top to avoid any accidents during testing. Here on the left-hand side are the 3 current measuring circuits, and then starting on the top on the high voltage and then leading into the bottom portion here, these are the 3 voltage measuring circuits. This square here is where the 5 volt to 9 volt regulator will go. It takes the 5 volts from the power supply and gives it to the Rogowski coils. Here on the right hand side is the 5 volt to 3.3 volts regulator, which will be in charge of powering the MCU. And then here on the bottom, as part of our power path system for battery backup, is a 3.7 to 3.3 volt regulator. It takes 3.7 volts out from the power path chip and then turns into 3.3 volts for the MCU. Shown here is the 3.7 to 3.3 volt regulator that we're using to give the power from the power path system to the MCU in case of a power blackout from the panel. Shown here on the left is the schematic. We are using the LM3671, and here on the right is the PCB. When designing this PCB, we took all considerations from the datasheet, such as keeping all the components close to the regulator chip, as well as consistently keeping a power flow from the input capacitor C2 into the V-in pin, through to the switching pin, to the capacitor L1, and from there to the output capacitor C1 in a constant loop for the current. Shown here is the 5 volt to 3.3 volt regulator that we're using to take 5 volts that is coming from the power supply and turn it into 3.3 volts, which is used by the ESP32. Shown here on the left is the circuit schematic for the regulator. We're using the LM2594. Shown here on the right is the PCB. And when designing this PCB, we took into considerations such as using wide 20 mil traces in order to improve current flow throughout the circuit, and placing the inductor L2 as far from the regulator IC chip as possible, so that way we didn't have any magnetic field feedback. Shown here is the 5 volt to 9 volt regulator that is taking 5 volts from the power supply and turning it into 9 volts in order to power the Rogowski coils for the current measuring circuits. Shown here on the left is the circuit schematic. We are using the LM2735Y, which has a lower switching frequency than its LM2735X counterpart. Shown here on the right is the PCB design. When designing the PCB, we took into considerations from the datasheet, one of those being to keep the ground plane away from any pads of the switching pin, as well as ensuring that the C-out capacitor is close to the ground pin and the outputs of the regulator, and the ground pad from the regulator be connected to the ground plane with 2 vias for improved stability.
So this is our software block diagram. We have data sent from phase circuits 1 through 3. If the system is single phase, we set it to single phase mode, and if it's 2 or 3 phase, we set it to the respective mode. The MCU then reads voltage and current from circuits, and the MCU calculates power consumption. Then the MCU sends voltage, current, and power data to the SD card for storage. If there is a usable Wi-Fi connection, we'll use Wi-Fi to send it to the data to that website and application for real-time monitoring. And if not, we'll use a USB. If there's already 30 days worth of data, we'll delete the oldest data row and add a new row. And if not, we'll just add another data row. So for our backend, we chose Node.js. It enables developers to use JavaScript for backend tasks, creating APIs and real-time applications. It's cross-platform. You can use it on Windows, Mac, etc. And you can generate dynamic page content with it, handle file operations, collect form data, and interact with databases. The main reason we selected this is because it's ideal for real-time applications and integrates seamlessly with MongoDB and front-end JavaScript, which is what we're using. We didn't pick a PHP because it's not optimal for real-time sensor data handling. So for our front end, we chose JavaScript, HTML, and CSS. HTML is used for the structure, JavaScript for interactivity, and CSS for styling. There's extensive documentation and resources available, and it's widely supported by all major browsers. We chose JavaScript, HTML, and CSS because it's simpler to implement and maintain, while React, on the other hand, is just kind of overkill for how simple our website will be. So for our database, we chose MongoDB. It's great for storing large amounts of data if needed. It can be developed across multiple cloud providers such as Google and AWS, and it provides fast query speeds. The reason we chose it is because it's ideal for logging frequent sensor data like voltage, current, and power readings in a flexible and scalable format. For MySQL, we didn't pick it because it's less optimal for flexible or fast-changing sensor data. So this is the UI of our website for the sign up and login. So here we have your created account. If you already have an account, there's a link that will take you to the login page. And here's the login page. If you enter a password incorrectly, a prompt will come up telling you it's wrong. You also have an option to change your password, or if you forgot your password, to get an email and change it. This is the UI of our website, the dashboard. The circles showing the voltage, current, and power will be acting as a real-time monitor system, receiving data constantly from the logger. When a single-phase system is connected, there will be 2 rows of data, one for phase 1 and one for phase 2. When a 3-phase system is connected, 3 rows will show up. We also have a download PDF button, and when clicked, it will download a report containing the last 30 days of data to comply with the NEC requirements for permitting.
Currently, this is a sketch of what we want our 30-day report to look like. This is currently AI generated. It will show graphical values on the top for voltage and current. That way you can check every single peak with time and date. And then if you see consistency around the same time, you can look for the specific date and hour, which will be on the bottom for every 15-minute recording that is sent to the logger. And finally, at the end of the report, there will be a note that explains when was the highest peak since the installation of the device. This is done so if in a 30-day report, the highest power peak is only 15 kW, and 3 months before that day, the highest power peak was 50 kW. The engineer looking at this data can make the decision to use the highest power peak, as he knows that sometime before it was higher than the 30 days report that he's looking at the moment.
Here we present the budget overview for the WattsWatch project. Our initial allocation was $2,000. We've spent approximately $1,190 to date, leaving us with around $810 in remaining funds. Major expenses included the Rogowski coils with 528, which were essential for accurate current measurement, and the remaining funds are reserved for enclosure fabrication, additional testing, and last mile integration. For this project, we established clear roles and responsibilities among the team. Daniel brought in great background knowledge in the electrical field while also helping in prototyping, hardware enclosure, and voltage and current measuring circuit testing. Juan took the lead in circuit design, PCB layout, and helped coordinate testing protocols with Daniel. I'm contributing to PCB design and hardware integration while also helping managing scheduling and administrating the budget. And Ethan managed the full software stack, both the front end and the back end development, and he built the website interface and handled all the database integrations. As of our latest checkpoint, we've made strong progress across all major project areas. The current transformers and voltage circuits have been fully prototyped and tested, ensuring that they are ready for PCB fabrication. PCB development is about 70% complete, with our main board and regulators designed and fabricated, now entering the testing phase. Software development is about 50% complete, and hardware testing is about 75% complete. Overall, we estimate the system is about 70 to 80% complete, with remaining work focused on enclosure design, extended stress testing, and final report generation. For the plan for completion, we designed a schedule to be able to meet all deadlines. We have our PCB components ordered and received. By the 15th of June, we want to have fabricated the PCB and have all testing completed so we can integrate the software. By the 30th of June, we want the build enclosure designed and finalized. That way we can test on an existing panel. For the next day, we want to be able to start data collection. That way by the 20th of July, we can generate our final report. Thank you for tuning into our CDR review for our WattsWatch Power Logger. We look forward to answering any questions that you guys may have.